Okay, so the next speaker is Vincent Humilière from Paris, and we talk about action of fixed points and spectral invariants of Hamiltonian homomorphisms of surface.
Okay. Thank you very much for inviting me. For me, I mean, it's the first time I participate to this workshop. To me, it's a kind of a legendary workshop, so I'm very happy to be here. And also to have an occasion to work on the French National Day. So thank you for that. Okay, so I'm going to talk about some joint work with Lev Buhovsky and Soban Seyfadini. This is very much in progress. And the problem we are interested in is to understand whether on surfaces the spectral invariance for Hamiltonian homeomorphisms whether they are spectral. Okay, of course, they are spectral for diffeomorphisms, and the question is whether they are also spectral for homeomorphisms, and I will give a precise meaning to this soon. So I don't have anything like super spectacular to present, but we have some partial results which are already good for some applications. So yeah, that's the plan. Okay, so maybe some context. Let me recall the story of the Arnold conjecture for homeos. So first, what do we call Hamiltonian homomorphisms? It will just be homeomorphisms which are C0 limits of Hamiltonian diffeomorphisms. Okay, so definition. Hamiltonian homeomorphism is a C0 limit of Hamiltonian diffeomorphism so in dimension 2, in fact, there's maybe a more pleasant definition on surfaces. These are exactly homeos which preserve the area, which are connected to identity, and which have zero flux. Okay, in dimension 2, we can define flux in a C0 context. And so this is these are exactly homeos which preserve area, which are connected to the identity, and have vanishing flux. Okay, in higher dimension, there's no such nice description, but so we keep this as a definition. Okay. Okay, and in this context, there's a theorem that says that the Arnold conjecture holds. What does it mean? For any Hamiltonian homeo phi, yeah, on a surface, sigma, for the whole talk, sigma will be the surface, okay? If I forget to repeat it. Then the number of fixed points, I could say contractible fixed point of phi, is at least 2 if sigma is a sphere, and that's a theorem of Frank's. and it's at least 3 if sigma is a surface of higher genus. I only consider the case of closed surfaces, okay, with G at least 1. Okay, and that's exactly the lower bound which is predicted by Arnold conjecture. Okay, so in that case, on surfaces the Arnold conjecture holds. But if we go to a higher dimension, there was this example that we built with Lev and Soban in some years ago already, that saying that if you take any symplectic manifold of dimension at least 4, then we can find a Hamiltonian homeomorphism with only one fixed point. There exists phi, a Hamiltonian homeo, with a single fixed point. So this thing, this Arnold conjecture fails for homeos in higher dimension. Okay? But on the other end, we realized shortly after, maybe I should first introduce some things. Yes. Yes. Sorry. So we realized that somehow we could still have some kind of lower bound of Arnold type if instead of counting fixed points, we count spectral invariants. Okay? So I'm going to explain. So maybe just recall what are spectral invariants, or maybe I won't say what they are, but still recall something. Let's assume for this, for a moment that that omega vanishes on the pi 2 of m. Okay. Then in that case, spectral invariants are maps that I will denote rho sub alpha that go from the Hamiltonian group of M to R. And okay, and you have one for any alpha, for any homology class alpha, okay, which is non-zero. Those are maps like that, so real numbers associated in a canonical way to any Hamiltonian maps. So strictly speaking, there's a normalization problem that I will not talk about, but it's not, maybe it's not spectral invariants which are maps like that, but maybe difference of two spectral invariants are maps like this. But let's not worry about that. And they are spectral, which means that they take value in the spectrum of phi. So for any phi, rho alpha of phi belongs to the action spectrum of phi, which means it's the action of a fixed point for some fixed point x of phi. And here H is the Hamiltonian which generates phi. Okay? H1 equals phi. So that this property, the fact that spectral invariants are actually the action of some fixed point, this is what it means to be spectral, and that's what we are kind of wondering in the case of homeos. Okay. And another feature of this invariant is that they extend the fact that these functions extend to the C0 closure of Ham that I will denote this way. Okay, they extend to the C0 closure of Ham. So they extend to the group of Hamiltonian homeomorphisms. Okay, and so they are well defined for homeos as well as just by continuous. Okay, and so now the problem is really whether this extension still satisfies something like this. Okay. Where is the? It's here. Yeah, again, maybe I should not write it this way. It's not this that extends; it's the difference of two which extend. Okay, maybe. There are some normalization problems that makes it otherwise false, but this extends to the closure. Okay. Yeah. Otherwise it's just not defined. Actually, okay. Okay, and so to finish with the story of the Arnold conjecture, what we proved at that time is that still under the condition that the manifold is aspherical, symplectically aspherical, omega m. We prove that if the Hamiltonian homeomorphism phi has finitely many fixed points, then the number of distinct spectral invariants will satisfy Arnold type estimate. So it's going to be bigger than the cup length of M plus 1. Okay. So let's not worry about what is the cup length. But this is somehow one version of the Arnold conjecture that there should be a lower bound like that. And but what's interesting here is that we can it could happen that we have only one fixed point, but still those numbers will be all many of them will be different. Okay, so it shows that in dimension one comment is that in dimension at least 4 there's no hope to have some kind of spectrality. First of all, we don't know how to define the action, but there's no hope because you see here you have only one fixed point, but somewhat different possible action values. So no hope to define action, or yes, to define action in a reasonable way. And okay, so that's why we are focusing now from now on. We will focus on the case of surfaces in dimension 2. So, for example, what was our motivation at the beginning of this project is whether we could, using this, recover the theorem of Matsumoto and Franks. It would be like a purely symplectic proof because those proofs are done with some dynamical tools that personally I don't really understand. And so our motivation was to give a purely symplectic proof of this. Dimension 2. Okay. Yes?
What do you mean in the emission rate reasonable for no hope to define action?
Yes.
I think that was why not?
So you want me to repeat?
Why?
Why?
What's the difference between dimension 2 and dimension
Okay, because this counterexample here to the Arnold conjecture, it's only in dimension at least 4. Okay, there's really a dichotomy. But in dimension 2, we have Arnold conjecture. Dimension bigger than 2, no Arnold conjecture. But still, there is this estimate here, and that says that there's no hope also to define action. Okay. Yeah.
Because you don't know how to define.
You have to speak up.
Because you don't know how to define action, or because you don't know what you should be.
First of all, I don't know how to define action in dimension 4. And second, I think this story tells you that there's no hope to have something reasonable, like spectral invariants won't be spectral.
When isolated fixed point,
Yes.
do you have local homology well-defined?
In higher dimension, I don't think so. Well, I don't know. I don't know, but I remember that when we were thinking about that this period of time, it was not clear. We tried, and yeah. Okay.
Sorry,
yes.
The question is more or less, I think, related to Victor's question. So you don't know if this example is somehow degenerate, right? Of course, it's anamorphic.
It's very degenerate. I mean, the construction is really you put all the fixed points at the same point in a, so I don't know.
No, but,
yeah.
but I mean, so what do you mean more precisely with degenerate?
It's a homeo, so I'm not sure how to.
Yeah, because in my mind is if you can define local homology,
Uh-huh.
then the local homology is not. It has a big rank. It ranks bigger than 1.
Yeah.
In your example, in this example, the homeomorphism is smooth everywhere but at one point.
Yes.
So in this case, you really pack all the homology. In this case, the homology is defined there.
Yeah. Yes.
Yeah.
That's what happened. We managed to sort of contract everything in one point. But,
does it make sense to define the local homology as a directed limit?
I'm not sure. I mean, the fact that it's a C0 limit, then you have no control. I mean, the usual way to define the local floor homology doesn't work. That's sure. And then, I don't know. Yes. Yes, that's a good point. Yeah.
Because there's no action.
Yeah. In this case, sorry, it's not local anymore because the action is
Yeah.
distinct.
Exactly. Yeah. Okay. So now I want to say quickly how to define action for Hamiltonian homeomorphisms. So that's not that's something that has been done by people in dynamics. Action for Hamiltonian homeos. So I think that the first it might have been a bit folkloric before, but I think the first time it was written was by Wang, Jan Wang. I don't know if you know him. It's a former student of Patrice Lecalvez. And the version I'm going to present is a modification of even in the end it's equivalent, but it's a differently presented definition by Leroux and Wang, which is it's still in progress. Okay. And okay, so we pick phi to be a Hamiltonian homeomorphism on a surface. So that's my notation for homeomorphism, the bar. Okay. Where am I? Okay. And let's pick x and x prime, 2 fixed points of phi, and I will assume that they are contractible as usual to define the action. And we need to choose an isotopy I, which generates phi. And we also need to choose a curve gamma from x to x prime, from x to x prime. And I will first make an assumption. Assume that this isotopy I fixes x and x prime at all time. Fixes x and x prime at all time. Okay? Different page. And then I'm going to define a number, which I will denote like that. I of phi x and x prime will be the integral over all sigma of, so I want to consider the intersection of this curve gamma that's the curve gamma. Consider the intersection with the isotope, the orbit of a point z. So I consider a point z somewhere on the surface, and I consider the isotopy. Okay, phi of z is here, and this is the path I of z. Okay. We consider this intersection, and we record the algebraic intersection number between the two. Okay, and we integrate it over omega. So I'm not sure how I should. I don't know, omega z like that maybe. I don't know. Okay, and we integrate over all the surface. So basically, what we are defining here is the flux of this isotopy I through the curve gamma. Okay, that's called of I through. So it's not always defined, but there's a lemma that Leroux and Wang prove that if x and x prime are isolated, then there exists a curve gamma such that this number here is bounded. Maybe I should denote it rho of z, such that rho of z is bounded. Okay. And then they also prove that this number does not depend on the choice of gamma, for which it is defined, up to wait. No, here in that setting, it doesn't depend on the choice of gamma. Okay. And it also does not depend on the isotopy I. Well, if the surface is not the sphere. Okay. And then there's a, I don't know, the fact that this thing does not depend on choices. So the choices are gamma and I, but there's a specific case where sigma is equal to the sphere. And in that case, it doesn't depend on the things, only modulo 1. Okay? Where 1 is the area of the sphere.
I'm sorry.
Yes?
Are there any assumptions on the smoothness of the isotope?
No.
So any continuous isotope?
Yes. It has to be Hamiltonian here. Yeah, but I mean, phi is, yeah, any continuous isotopy. That's purely a topological construction. Yes, I think that's how you would define it rigorously. But that's some kind of, yes. homological intersection. Or
What of Z? Which number?
yes, but yeah, somehow you don't. I mean, this is invariant by homotopy, so that's but if the homotopy doesn't cross the endpoints, okay, that's the okay.
What did you write that only mod 1?
Sorry. Here, so there was this fact that it doesn't depend on choices. It's not exactly true. It's true only for surfaces of higher genus, of genus at least 1. And for the sphere, it's only, this number doesn't depend on choices, mod 1. It's modulo 1, where 1 is the area of the sphere. Maybe that was the missing information. Okay. Okay. And in fact, in that case, this is going to be the difference of action between x and x prime. Okay. Maybe I don't want to say how, in too much details, how to define the same number when I mean, here we did some assumption. We assume that I fixes x and x prime. So this is some kind of unlinkedness assumption between the fixed points. When the fixed points are linked, it means along the isotopy one turn over around the other, then we cannot find such an isotopy. But somehow the idea is to lift to the universal cover and then give the same definition on the universal cover, because on the universal cover you can find an isotopy that fixes the 2 points, because you're allowed to make a full turn. I don't know if you see what I mean. Okay, the idea is, maybe I just say this. When the points are linked, we do the same construction, but in the universal cover. And that's how we define this number I of phi, x, and x prime. Okay. We integrate over the whole thing, over the universal cover, but it's going to be 0, yeah, almost everywhere. Not almost everywhere, but outside the compact set. Okay. And then there is some, some property. Phi. That this is 0. And so there exists some function a phi such that I of phi x y is a phi of y minus a phi of x as a consequence. Okay, and this is defined. I mean, we had this assumption here that the points are isolated. So this function is defined. Now the assumption that all points are isolated. So if phi has finitely many fixed points. So here, in fact, they prove much more, but somehow I'm reducing to this very particular case. They define a notion of bounded fixed point. Those are the points for which the action can be defined, basically. And they show, for example, they show that it's always true that the points for which action can be defined are dense in the set of all fixed points. Okay?
So what is action?
Well, this is difference of action.
Different action.
Okay. And, okay. But I will stick to this case where we have finitely many fixed points. Okay. So now I'm going to state something. I can state it here, theorem. So we assume that we have a Hamiltonian homeomorphism with finitely many fixed points, and then the spectral invariant will be spectral. So let phi Hamiltonian homeomorphism on a surface with finitely many fixed points. Maybe I can say well, let's say fixed point, but we only need finitely many contractible fixed points. Then, so of course, this action function is only defined up to a shift by a general shift by a constant, right? So here, the action can be chosen so that for any alpha, for any homology class which is not 0, rho alpha of phi is equal to a phi of x for some fixed point. That's the spectrality for in this very specific case where you have finitely many fixed points. So now I said that the work is really in progress. It's because we are trying to somehow relax this condition, finitely many fixed points, and we are trying to see. I don't think we will manage to go to the very general case, but we are trying to still relax this condition and see how far we can get. Okay, and then we can write some corollaries. So the first corollary is that we recover the Arnold conjecture for Hamiltonian homeos. So we recover it. So the Franks and Matsumoto theorem follows from this and the previous result. Right? There was this result on the number of spectral invariants, remember? And if you combine this with the fact that the spectral invariants are actually action values, then it shows that the points must be different too, not only the spectral invariants. So you get the lower bound for the number of fixed points. Okay? So that was the initial goal. Now we want to go a bit further. So to find more applications, I think we need to be more general with these conditions. But we can still say something on for pseudo rotations. So we let phi to be C0 Hamiltonian pseudo rotation. On S2, which means that this is a Hamiltonian homeomorphism, which has exactly two fixed points and no other periodic points. Two fixed points, no other periodic point. So, for example, an irrational rotation on a sphere. Okay. But there are some more complicated examples. And then we show that these things are gamma spectral. Then there exists a sequence of iterates ki, which goes to infinity, such that phi ki gamma converge to identity. Here, gamma means the spectral norm. which is defined as, maybe you know, as a difference of spectral invariants. Okay.
So in the smooth case,
Yes.
this, one could say something about the, one can be quite explicit about the sequence of spectral invariants and the
I think I know what you're referring to, but I haven't thought about it. But okay, let me just mention that it's known in the smooth case since the work of Ginsburg and Gürel. But they prove much more. I think they prove the case of CPN, and they prove some kind, I'm not sure exactly, but I think you also have some result for C0 convergence to identity. Maybe not to that generality. Maybe you need to impose something on the rotation number, but okay. And you also have some result on the number of on which iterates, but I don't know. I haven't thought about it. But I can say more. In fact, what we have is that in this setting, the distance, when we add gamma of phi to the n, then this is going to be the distance of n gamma of phi to z.
yeah, that's exactly what I had in mind.
Okay. Okay, great. And okay, so maybe I could explain an argument for that, and then I will give some ideas on why this is true. Okay. So the proof of the corollary. So there's a first fact is that the pseudo rotation, they are known to have a well-defined rotation number. So that you have the two fixed points, which are let's say the south and north pole. Then all the other points, they have a rotation, asymptotic rotation number, which will be always all the same. Okay. I have a well-defined rotation number. Denoted by rho. Okay. And consequence of it is that if you consider this number I and S, you know, so remember this number that I defined earlier, which was the flux through a curve joining the two fixed points. Okay. Then this is going to be rho, or maybe minus rho, modulo 1. Okay. Now, by spectrality, so this new thing here, okay? What we know is that gamma should be a difference of two spectral invariants. And so we know that gamma of phi, I'm breaking all the jokes, I'm sorry. Gamma of phi should be either this number or maybe this number. Well, it could also be this number for this number, modulo 1. These are the only, modulo 1, that these are the only possible difference of actions. Okay. And there's a result by Kislev and Shelukin. That says that gamma of phi should belong to 0, 1/2. Okay. And that will constrain many things. And we also know, actually, since phi is not the identity, we know it cannot be 0 because there is the non-degeneracy of the norm. Okay. So from this, I know it can't be this, it can't be this. Okay. So this is either this differential action or this differential action. So gamma is a plus or minus rho modulo 1. Okay. And now, since it should be also between 0 and 1/2, in fact, this is the same thing as the distance between rho and z. Okay, gamma of phi is computed in that case. Okay, and now we are almost. We are basically done. If there are two cases, if rho belongs to 0, 1/2. Mod 1, then we can write that the distance between n gamma phi and z is the distance between n rho and z, which is by the above gamma phi n, because phi to the n is also a pseudo rotation. Okay. And we do something similar if rho is in the other side of the interval. If rho is in 1/2, 1. Okay, we do something similar. But in all cases, we get what is here. Okay. Any question? So maybe that's an illustration that somehow we can, once we have spectrality, we can put to the C0 case many proofs that that we know how to do in the smooth case. That's the okay. Now I want to give some ideas on why this is true. Ideas for the theorem. Okay. So the idea is that we need to find good smoothings of phi, because the spectral invariants of phi, remember, they are defined as a limit of the spectral invariance in the smooth case. Okay, so we need to find a good smoothing. So we need to find a smoothing theta of phi. So phi here is this. There's a homeomorphism here, such that if we take a fixed point of phi and a nearby fixed point of theta, then the action of well, maybe I should y. The action of y for theta will be approximately the action of x for phi. Okay, so we want to find some smoothing which is friendly with action in some way. Okay, in general, if you do a random smoothing, okay, if you make a C0 small perturbation, then the action can be whatever. Okay, so we need to do it in a gentle way so that the action is preserved. Okay, and once we have that, then we are done because we take a sequence of such smoothing. The spectral invariant, maybe I should write. Then if we have this, okay, if then we get a sequence, a smooth Hamiltonian diffeomorphism which converges to phi, and we know that then the spectral invariance will converge to the spectral invariance of phi. So Igor will recall me that it's not the spectral invariance, but the difference of spectral invariance, but let's not talk about that. And so these things converge. And we know by spectrality in the smooth case that this is some action, action of theta n for some yn. And then we pick some subsequence of yn which converge by compactness. Okay. And if I consider yn converge to x, then this will converge to, if this is true, what I hope to have, then I will get that it will converge to this, and so we obtain the spectrality we want. Okay? So we want to make this gentle smoothing. Yes.
Are you looking for some smoothing? There may be no fixed point nearby.
Yes, it could happen that there's no fixed point, but here I'm assuming that if there is a fixed point nearby, then yeah, it should, yeah. Yeah. Okay. Okay. So just a picture so that you can see where the problem is. Let's assume I have 2 points, x and x prime. I want to somehow compare the flux for phi with the flux for theta through a curve like that. Okay. And what happens is that if I have a point z and its orbit that go to phi of z, and if I take any smoothing, then I can find an isotopy which is closed, and it will end close to z. And in that case, on this picture, we see that the intersection number should be the same for phi and theta. Okay, but this is not. This is the case only if you're far from x and x prime. Okay, if you're close to x and x prime, then you might have things which rotate like that. Okay, and then even if you make a C0 small modification, then the intersection number has absolutely no reason to be close to it. Okay, so somehow we want to isolate in some way the contribution to this. The contribution of these neighborhoods of the fixed point, so that they are not annoying. Okay. Okay. So let me now give you the strategy. So the first step will be to find a smooth perturbation psi of phi. Phi is the initial map, okay, and a family of disks which are disjoint. And I will denote by D their disjoint union. It's a finite, well, they all have the same area, in fact. Okay. It's a finite family of disks which are disjoint, and such that psi of D equals D. And it's smooth, but it's a C0 perturbation of phi. Okay. It's going to be the first step. Maybe I give the whole strategy, and then if you want some, I mean, I won't be able to give all details, but if you want, I can still give a little more detail at some stage for some steps. Okay, then we pick a function f, which is positive, such that f is psi invariant. So psi is the new map, the one that preserves the disks. And we want f to be approximately 1 on D. Well, no, that's not what I want. Sorry, it's going to be very, very small, so approximately 0 on the complement of D. Okay. But I still want f to be, I forgot an important condition here. Let me go back. I want these disks to fill up almost all the area. Okay, so then area of D is approximately the area of the whole surface. Okay. Otherwise, it's not very difficult. And now, okay, and now I want my function here to be approximately 1 in the L1 norm. Okay, so you need to think of f as an approximation of what's the word for that? The indicatrix function. I don't know how you say in English. The indicatrix function of D. Okay, but I want it to be strictly positive still. Okay. Okay, and now the point that the fact that f is psi invariant implies that psi belongs to is symplectic for f omega, not only for omega. Okay. And we can somehow make some adjustment to make sure that the flux is 0. And then this psi will belong to ham of f omega. Okay? And then the last step is to use some nice lemma, which we could call quantitative Moser lemma. That's something that says that if for every epsilon positive, if f is sufficiently L1 close to 1, then there exists H such a diffeomorphism, maybe I should say diffeomorphism, that pulls back f omega to omega. I forgot one condition here. I want integral of f to be equal to 1. Otherwise, I won't be able to apply my Moser lemma. So So we have this, and that's now comes the quantitative part. The C0 distance of H to identity is smaller than epsilon. Okay. So somehow it says that if we have two symplectic, two area formed on the surface which are L1 closed, then we can transport one to another with a C0 small map. Okay. Okay, and now we define. So that's the define theta to be H inverse psi H. So we use this H. We conjugate this psi with this H, and we get something which is Hamiltonian with respect to omega. So this belongs to Ham omega, sigma omega. Okay, and this is the theta which is going to be the good smoothing, the good smoothing that we are looking for. So I can maybe use 2 minutes to explain why roughly this works. Are there any questions? I can't hear you well, sorry. It can...
It's very close to 0 in the complement
Of D, yes?
Yes, but it's L1 close to 1.
Yeah, because the complement of D has very small area. That's here. Yeah, but when you write integral of f minus 1 omega, omega, right? This is a small only on sigma take away D. So this will contribute to epsilon to this area, to this integral. Okay. So why does it work? I mean, of course, what I'm going to write is not purely rigorous because, I would need to put 10 quantifiers and write things in the exact precise order, but that's roughly the idea. If I look at the flux of phi between x and x prime, okay, and I will put an omega here so that it's clear that it's the flux with respect to omega, okay? Then this is by definition, it's an integral over sigma of gamma intersect the isotopy. I will write it this way to say that it's the isotopy for phi. And we integrate with respect to omega. And then, since the disk occupies almost all the area, and since this thing is bounded by what we saw earlier, by Leroux and Wang, okay, then this is the same, it's roughly the same as the integral over D. And here we are already happy because somehow we got rid of what happened near the fixed point. And then I can smooth the thing out. And since we are far from the fixed point, then I can say this is the same thing as I psi of z with respect to omega. Okay. So maybe it's not, maybe I need to, since it's not exactly the same fixed point at the end, maybe I need to change a little bit my curve so that this makes sense. Okay. And now I can choose my f so that this is the same thing as, this is approximately the same thing as the integral over sigma of the number of the same thing, sorry. but with respect to f omega. Okay. And here, what we see is just the flux with respect to f omega of psi between maybe not x and x prime, but some nearby points. Okay. And now this is the same thing, just by conjugation of the flux of theta between h of y prime. Okay. And since the this shows that the flux of phi and theta are closed, and so the actions are closed. And that's that's roughly how it works. But of course, I mean, it's you have to be very careful with the order of quantifiers, and I'm not saying this is completely, but that's roughly the idea. Yeah, so I think I'm going to stop here. Thank you.